So now we will look into the application of XRD in cement based materials, right. So why XRD for cement? So provides information on individual phases in cement and hydrates. You can find out what do you have in cement, what do you have in hydrates, right. Quantitative phase, quantitative analysis can be done, we have seen that. This also we have seen, crystal structure determination, this all goes back to the principles of X-ray diffraction, right. Also we can use that information to describe hydration kinetics, you can monitor the hydration, right, mechanism, and also we can use it to identify the degradation mechanisms such as sulfate attack, delayed retinite attack and thermocyte attack. These are few examples. Okay. So first of all, any how do you report this X-ray data collection? So you have to get the X-ray diffraction pattern, right, from X-ray diffractometer. So usually what you see when you read any paper, or even if you have carried out your work, these are the things you have to report. You have to either in publication or in a report see what equipment did you use, what was the geometry, what was the X-ray source, what was its wavelength, because that will affect your diffraction pattern. If you use different wavelength, that will also affect the peak position, right. We know that it is all related to lambda. So these are the things you have to keep in mind when you report the data, right, or you see the data, you will see that okay, this data was obtained using this instrument for this geometry with this wavelength, things like that, right. Then important is scanning parameters, very important, right. What are the step size, scanning rate, what was the 2 theta range, in this case you see 5 degree to 7 degree 2 theta. So these are the common things you have to report. Okay. Measuring time.
Backloading, side loading.
Yeah, these are the ways you load sample, as we did not go in detail, like backloading, as I said, you flip your sample, then load it just to make sure that, yeah. So front, you are loading the front, side is side again, right. So there are different ways to load the samples.
To make the sample compact.
Yes, yes. Yeah, you have to obviously make a compact sample, but also you have to make sure that there is no preferred orientation. Okay. Depending on the sample, you may not even have preferred orientation, but since we are talking about the cement system where you have calcium hydroxide and etrinite, and you tend to see preferred orientation, right. So what does typical X-ray pattern of cement look like? So obviously we have plotted here different types of cement. So let us look at the PC. You are familiar with the Portland cement, right. This is the PC, Portland cement. So you see basically different peaks, right. That tells you what kind of which phases are present in your cement. Gypsum, C3S, this is elite, right, C3S, you have C2S, sometimes it is yeah, maybe it is somewhere here. So yeah, these are the major peaks, right. Different cement. So this is CSA cement, calcium sulfoaluminate cement, CSA. Okay. I mean, just idea is you can get an idea about the phases present in your cements, right. If you resolve all the peaks, you will be able to tell what are the phases, and depending on the system you will have different phases. This is calcium alumino Ca cement, calcium aluminate cement, and this is white Portland cement. Okay. So you can get an idea about the phases present in your cement by looking at X-ray diffraction pattern. What are the principal peaks, right? So this is a table you can see, so you often see these kind of phases like calcite, for an example, calcium carbonate. So the peak, so first is, this is the D value, this is intensity, this is 2 theta, basically it is in the order D, intensity, 2 theta, right. You have a pattern, this is the X-ray diffraction pattern of calcite, and this is the strongest peak, second strongest, third strongest. This gives you an idea what are the possible phases, like principal peaks in the cements, right, 3 peaks. You should always check for at least 3 peaks when you want to make sure a particular phase is there. So you can go over this list, you see that C3S, right, you are familiar with this tricalcium silicate. So, the primary peak is, the strongest peak is at 32 degrees, 2 theta degrees, right. B light C2S, C3A has two forms, right, 3 cubic, monoclinic, orthorhombic, crystal structure basically, C4AF, gypsum. So, these are the common phases you encounter in your cement, right. You can identify your phases based on the peak positions. Also you can see intensity, how it is varying. Again, like if you are doing quantitative analysis, you want to get the appropriate PDFs, powder diffraction file. These are some the common PDF codes, right. Also you see ICSD codes for the phases present in the cement. See elite, which is C3S, right. Depending on its crystal system, you have different files, right. Bilite, aluminate, ferrite, portlandite. So, these are the common phases present, right, and when you do qualitative like quantitative analysis, you have to get these files from the database, right. This will be also useful for your assignment. When you have to look for the phases, you can just get these PDFs, then see if it matches with what you have in your sample, right. So, what are the issues in cement XRD? See, copper K alpha radiation can cause iron atoms to fluoresce. So, this can submerge low intensity lines as for C4AF. So, cobalt K alpha, this is another example, cobalt K alpha may be a better choice here. There is a lot of overlap among principal amounts. When you actually look at your XRD diffraction pattern, you will see a lot of overlap, right. Also you have a multiplicity of polymorphs. What do we mean by, so C3S for an example, right, has 3, so monoclinic M3, T3, T, depending on the temperature, you have these polymorphs, and through XRD you can detect that. See the X-ray diffraction pattern, what are the changes? So, decrease in the symmetry, usually T means triclinic, M is monoclinic, you are decreasing in this direction, right, in the symmetry leads to increase in diffraction peaks. So, if you look at the triclinic one, you see more peaks compared to monoclinic one. So, idea is you can use this X-ray diffraction pattern to identify these polymorphs. Also you can use this X-ray diffraction, we are looking at now application, right. So, one thing is X-ray diffraction can be used for phase identification, X-ray diffraction can be used to identify the polymorphs. Also you can study or you can use X-ray diffraction to examine the effect of sample preparation. If you want to compare different techniques, you want to see okay which one is better, which one is worse, you can use the X-ray diffraction. So, here you see an example where we have compared you see on the left plot X-ray diffraction, fresh slice polish. So, the way you treat your just see when you use solvent exchange, for an example isopropanol slice polished, right. So, only difference between these two samples are one is treated with isopropanol, right, one is not. So, what do you see? You see if you look at now eternite peak, the intensity has reduced significantly. So, you can just using X-ray diffraction you can tell that your eternite phase may have gotten affected through this treatment, okay. So, where you can quantify it also on the right plot, you see here we have amounts like anhydrous amounts. So, you can see how the sample preparation affects your amount. But again this long exposure of isopropanol affects the eternite AFM phases, right. You see here this was for the 7 days of exposure. When you expose your sample for long time, right, that tells you that maybe that is not good for if you want to study the phases like eternite. So, a shorter solvent exchange results in less eternite and AFM decomposition, okay. So, basic idea is you can use this simple X-ray diffraction technique to understand the effect of sample preparation. You can compare different techniques and then find out which one will be best for your research or your work. This is again X-ray diffraction of cement. You see here this is high score plus high score software which was used here. Then you can see different phases. It can give you, when you do quantitative analysis, it can give you the phases like C3S, C2S, C4AF, how much of these phases are present, right. This is again Rietveld analysis, right. You can identify all the phases. This is the difference plot, right. You see idea is in Rietveld is you are minimizing the error between observed and calculated intensity. If it is very small, within the error, then it means it's how do we judge is goodness of fit, right? You want to reduce that. So here you don't see any, so what here happens when you carry out X-ray diffraction of cement paste, you start seeing this hump at around 29 degrees, right? This is amorphous hump primarily because of the calcium silicate hydrate, because calcium silicate hydrate is the main phase you get during the hydration of cement, but unfortunately it is not perfectly crystalline, it's a nano crystalline phase, right? You don't get a sharp peak. That poses challenge in quantification. Okay. Also here, if you look at the X-ray diffraction, this is the X-ray diffraction of 7-year hydrated white Portland cement. So white Portland cement. What is white Portland cement? How do you get white Portland cement? Without iron. Okay. Everyone knows what white Portland cement is, right? So obviously it has white color. So yeah, it does not have iron. So if you let in this test what they did, let it hydrate for 7 years, right? 7-year hydrated white Portland cement. So obviously you will see most of your phases like C3S has hydrated, so you have a CSH. So these are different phases, right? Pure phase, like phases. So you have, this is the combined pattern. The topmost is the combined. This is the combination of these phases. You see some C2S, because C2S is anyway slow in reacting. So you have some eternite, Portlandite, and you see the CSH, right? You see this kind of not sharp peak, right? Again, it shows you that the complex nature of the hydrates, right? Using X-ray diffraction, like using quantitative X-ray diffraction, for an example Rietveld, you can determine the various phases. In this case, you have a different cements where you have compared the Bogue analysis. You can also get the phase assemblage using Bogue formulation. Right? There is a modified Bogue formulation. Right? This is a Rietveld analysis. So there is a very close agreement between modified Bogue calculation and Rietveld analysis. You can identify all major phases: alite, belite, aluminate, and ferrite. That is the application of X-ray diffraction, right? You can quantify your phases. One important thing to keep in mind, see, when you are looking at the cement, it's fine, no problem. But when you are looking at the paste, when you are comparing 7-day-old paste versus 28-day-old paste, or 7-day-old concrete versus 28-day-old concrete, what is the difference? The difference is the degree of hydration. So what essentially happens, you start with your cement here. This is water, right? You are adding some water, then cement will hydrate. The amount of the solids will change, right? Your part of cement will convert to CSH, calcium silicate hydrate. See, so your solids, this will change, right? So when you are comparing, you have to normalize it, right? So normalization of Rietveld results is needed for comparing time series data. If you are comparing 3-day versus 7-day versus 28-day, then you have to make sure you have a proper normalization. You can't just take values from Rietveld analysis. So you have to back calculate. So this gives you some, these are some formulas you can use, like if you have a fresh sample, so you can normalize it by paste or by anhydrous amount, rescaled, rescale means the rescaled values, right. So obviously fresh samples and per paste, your rescaled value is close to Rietveld. But when you take into account anhydrous, when you normalize it by anhydrous, your water cement ratio plays a role. Dried sample, these are the formulas you can use. Idea is your degree of hydration is changing, your mass of solids is changing, so you have to take that into account. Using these relationship, you can normalize it, and then you will be able to compare. We can use X-ray diffraction to monitor the hydration progress, right. So in this case, you see hydration of Portland cement. What do we expect? The C3S will decrease in the amount, CSH will increase, or amorphous phase will increase. In this case, you have plotted various phases like C3S, C2S, C3S, C4F. What happens to these phases? So phases which are reacting, they will decrease, and phases which are forming, they will increase. So you can monitor the hydration using X-ray diffraction. This is again application of XRD to understand the hydration of OPC-CSA system. OPC-CSA is Portland cement calcium sulfoaluminate system. So, you can monitor the amount of, in this case, eternite with the time. So, you see when you have 30% CSA, eternite is much more than other, like this is 15%. So, you can compare different systems. Here you is the example of the quantification of eternite. Now, you know that we use mineral admixture, right, in our concrete. So, we can also study mineral admixtures. In this case, you see comparison between fly ash and slag, right. So, amorphous hump present in fly ash and slag is indicative of reactive nature of silica. So, in fly ash you see this amorphous hump usually is between 20 to 30 degrees, right. So, when you see this kind of hump, first thing which comes to your mind is amorphous nature, which we can use. That is the reason why we use fly ash, because then fly ash dissolves, it releases silica, reacts with calcium hydroxide and forms calcium silicate hydrate, right. So, this XRD can give you insight about that. See, in this case, here is a biomass ash, right, not exactly fly ash, but it has also amorphous silica. You see hump, which is indicative of your amorphous silica. This is the X-ray diffraction of raw powders, right. Here you have clay also, clay does not seem to have any amorphous hump, so crystalline in this case. Now, if you are using it with, this is a binder now, right, rather than going in detail, when you mix this biomass ash with lime, right, but you see formation of CSH. See, in raw ash and clay you do not have any peak at around 29 degrees, but binder, as soon as you add calcium hydroxide, you see the reaction between amorphous silica and calcium hydroxide, you see the formation of calcium silicate hydrate, right. So, you can get an idea about the dissolution of the amorphous phase, okay, by tracking the hydration. So, this is also application of X-ray diffraction. Also, see, we know that in cement we do not have any amorphous content, right, but when you let it hydrate, you form calcium silicate hydrate, then you see because just by nature of the amorphous nature of calcium silicate hydrate, which is not fully crystalline, you have amorphous content and we want to quantify it. So, you can use X-ray diffraction to estimate amorphous content also, right. For that you have to use internal standards, right. How do you do it? So, commonly used internal standards are rutile zinc oxide, right, and this is the formula given you can use. So, amorphous content can be written as this, where WIS is the internal standard in the sample. So, you are using internal standard. So, you know how much you have added. Suppose you are using 15% of internal standard. So, you know WIS is 15%, right. Now, you analyze your sample, the Rietveld, RIT is the, now when you perform Rietveld, it will give you some number, which will not be 15%, because it does not take into account the amorphous content, right, it assumes everything is crystalline. So, the RIT will be the Rietveld determined number, internal standard amount. So, when you know these numbers, you can calculate the amorphous content of your sample. It can also be used to examine the damage in concrete. Here is an example of thomosite attack. So, in X-ray diffraction pattern, like you have A you see presence of thomosite, T is kind of a attack. So, because see XRD pattern A showed formation of thomosite, which led to surface degradation of concrete, right. B on the other hand did not have thomosite, it had eternite. So, did not indicate it did not have that much damage in this case. This was a case study, right. But you see, these are few things you can identify using X-ray diffraction, but the challenge also is eternite and thomosite peaks are very close, too close, right. So, too close for differentiation. So, if you want to make sure that you have a formation of thomosite, you may need alternative techniques. So, it is always good to use alternative technique to verify, right. In some cases you will be sure, but when you are not sure, then you can use alternative techniques to verify your finding. So, this is the reference, I mean these are the references which were used. This is very nice, you should anyway we have this book recommended, right. So, there is a chapter on X-ray powder diffraction applied to cements, you will get more insights, like how do we use X-ray diffraction, and these are some papers which were used for this particular lecture. Okay. So, that concludes X-ray diffraction. So, we learned about the technique. We have learnt how it can be applied to understand the cement based systems.